Hello, my dear students. Welcome you all to Sri Jayendra Rank Zone classes. I am your mentor and your friend for the subject chemistry, and I will be taking the organic chemistry. My dear students, as you all know, we have started this chapter isomerism, this topic isomerism. And today, after discussing structural isomerism, I'm going to discuss about stereoisomerism or spatial isomerism. As you know, stereoisomerism or spatial isomerism is related to three-dimensional orientation of the atoms attached to the carbon. So stereoisomerism is a three-dimensional different representation of groups attached to the carbon atom. It is also known as spatial or space isomerism. Compounds having same molecular formula same molecular formula same connectivity same connectivity and structural formula and structural formula but differ due to the spatial arrangement but differ due to spatial arrangement of group or atom of group or atom are said to be stereoisomers are said to be stereoisomers. Understood? When we are talking about that the groups which are attached to the central atom, that is carbon, if their spatial or that their three-dimensional arrangement is changing, okay, so it will give rise to a new structure, okay, so that is known as what? Stereoisomerism. Although the molecular formula, the structural formula, the connectivity of the atoms, okay, remains same, is said to be stereoisomers, and the phenomenon is known as what? Stereoisomerism. It is divided into two parts, configurational and conformational. Configurational and conformational. Okay. So configuration isomerism and conformational isomerism. So first we are going to discuss about configuration isomerism. So according to configurational isomerism, the stereoisomers which are not interconvertible at room temperature. Stereoisomers which are not interconvertible at room temperature are known as configuration isomer are known as configurational as their configuration is changing. Okay, so they are known as what? Configurational isomers. So what exactly this configuration mean? Configuration simply means that the arrangement of the groups three-dimensionally it is changing. Spatially it is changing. Okay. So the stereoisomers which are not interconvertible at room temperature, they cannot be converted into one form to the other form. Although they have same molecular formula, same structural formula, and the same connectivity of the groups. but their arrangement, their orientation is changing, is known as configuration isomers. Okay. So this configurational isomerism is further divided into two parts, geometrical and optical. Geometrical and optical. So first we are going to discuss about geometrical isomerism. So geometrical and optical, they both belong to configurational isomerism. Okay, geometrical isomerism. It is a type of configurational isomerism configurational isomerism which arises due to restricted rotation of atoms or groups around a double bond system or a cyclic system. Around a double bond system or a cyclic system. Most importantly, the fact is, in a cyclic system and in a double bond system, the carbon is actually under more strain in comparison to carbon-carbon sigma bond. In a double bond system, as you know, the unhybridized p orbital of carbon, they overlap, parallel or sidewise or equatorial overlapping takes place. Because of this, the pi electron cloud is placed above the plane and below the plane. So above the plane and below the plane, the pi electron cloud, and because of these electrons, they repel the electrons of sigma bonded. Then because of this repulsion, the electrons or the atoms or the groups attached in a plane, they come up with this repulsion, they bear this repulsion, they tolerate this repulsion to move or to rotate. So because of double bonded system or a cyclic system, the maximum rotation they can go up to is 90 degrees. Okay. So the conditions for geometrical isomerism is restricted rotation, and the second is, because of this restricted rotation, they come up with different functional properties of the compounds attached along or opposite to the plane of rotation. To the plane of rotation. Is it clear? Okay. Now, for example, a carbon-carbon double bond it is not showing geometrical isomers? Because same group X and Y present on each carbon atom. So there should be an unsymmetrical attachment of the groups to the double bonded carbon. Like for example, if the double bonded carbon is having X and Y, then it will show geometrical isomerism. So restricted rotation is one of the condition. The second condition is different functional properties of the compounds. These functional properties because of the groups which are attached to it. Okay, so groups should be different. Understood? This is what the conditions of geometrical isomerism. Now, the fact is that this two carbon, when they are sp2 hybridized in case of carbon-carbon double bond, so this is sigma bond. When they make a pi bond with the help of unhybridized p orbital, I will shade this unhybridized p orbital with green. This is unhybridized p orbital. So these unhybridized p orbitals, when they overlap with each other, so when they overlap with each other, what will happen? The pi electron cloud will merge. Okay. There are three sp2 hybridized orbitals. Okay. Now, because of this, the pi electron cloud, they will merge. And because of this merging of pi electron cloud, the electron density, negative, 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 is more above the plane and below the plane. As the electron density is more above the plane and below the plane, the attacking reagent will attack either above the plane or below the plane or below the plane. So because of this, as the plane of the pi bond and the plane of the sigma bond is 90 degrees, the maximum rotation which can be come across is of 90 degrees. Okay, understood? Because the electron density is above and below, so they can maximally rotate themselves between the 90 degrees, 0 to 90 degrees. Okay, now geometrical isomers are geometrical isomers are named as cis trans, ENZ, syn and NT. Okay, so first we are going to discuss about cis and trans isomers. Cis trans isomers. When like atoms or groups attach at the same side of double bonded carbon atom, it is called as cis isomers. Okay. When like atoms or groups are on the opposite sides, doubly bonded carbon, they are called trans isomers. Are called trans isomers. Understood? Yeah. So carbon carbon double bond, A you can see the same group are attached on the same side of the plane of rotation. This is a cis isomer. Okay. And if I make this is a trans isomer. Okay, understood? So suppose this is the plane of rotation. This is the plane of rotation. Okay, and on rotating, when this B comes here, A comes down, so it will become trans like this. Okay, cis and trans. Malic acid, it's a cis isomer. Fumaric acid is a trans isomer. It is the trans isomer. Understood? Yeah. So there are many examples of cis isomers and trans isomers. What you have to stick to that the carbon-carbon double bond. Okay, if the groups are present on the same side of the plane of rotation, then it is cis isomer. If groups are on the alternate side, on the opposite sides of the plane of rotation, then it is the trans isomer. Now coming to E and Z isomers. Okay, this system is used for derivatives of alkene. Is used for derivatives of alkenes, in which all the four substituents should be different. In which all the four substituents should be different. Okay, like this is carbon carbon double bond, alpha, beta, A and B. If all the four groups attached to the carbon carbon double bond they are different, then it is basically applicable for E and Z isomerism. Understood? E and Z isomerism. Okay. Now, for E and Z isomerism, we have to go through the CIP rules, that is Cohen-Ingold Prelog rules. CIP rules. Cohen-Ingold Prelog rules. Okay. So according to these rules, the substituents on a double bond are assigned priorities. Are assigned priorities. Okay. The double bond is assigned the configuration E. E configuration is assigned to E, basically comes from antigen. Antigen. Okay. The German word for opposite. Antigen means opposite. If the two groups of higher priority of higher priority are on the opposite sides of the double bond, are on the opposite sides of the double bond. When we will come across the priority order rules, okay, first you understand that E configuration is given to that if there are two groups of higher priority, okay, if they are being more prior and they are on the opposite sides of the double bond, alternate sides of the double bond, then it is known as what? The E or antigen configuration. Understood? Now, I'll give you one example for this. This is carbon-carbon double bond, and I am numbering the groups which are more prior, like 1 and 2. Okay, 1 and 2. So you can see they are on the opposite sides. Okay, opposite plane. Okay, this is the E4. Now, Z configuration. Z means from Zusammen, Greek word which means together, means on the same side. If the two groups of higher priority are on the same side, of higher priority are on the same side of the double bond. So this on this basis we confine the E and Z configuration. Okay, on the basis of the the priority order. Okay, so now we will study about the priority rules. Okay, the example for Z form I will give like this. So you can see, okay, Z form. Now the priority rule. Cahill in gold and Prelog proposed a sequence rule. Proposed a sequence rule. Rule number one, which says when atom or group of atom which are directly attached to the when atom or group of atom which are directly attached to the stereogenic center to the stereogenic center have higher atomic number have higher atomic number will have higher priority. The one which is having the higher atomic number will be given more priority, will have higher priority. Okay, example. Okay, now you can see the highest atomic number of iodine, then bromine, then chlorine, and then fluorine. So you can see the groups, the higher priority groups, they are on the same side. Okay, so if they are on the same side together, Zussman means Z form. Okay, now NO2 and methyl. This is the most prior group. Okay, okay. Now you can see like 9F18, you know. Okay, the fluorine and NO2, they are on the opposite side. Mean E antigen, that is E form. Okay, so this is the Z form and the E form. According to the first rule, the group of atom or the atom attached to the stereogenic center having the higher atomic number will have the higher priority. They will show higher priority. Okay, understood? Now, The second rule says, rule 2, the second rule says that when the atomic number will be same, priority assigned on the basis of atomic weight. Priority will be assigned on the basis of atomic weight. Like C double bond C, deuterium. Now you can see the groups on the alternate side, that is opposite side, E form. Because the atomic number, if we talk about that D, deuterium 1, hydrogen 1, but the deuterium atomic mass is 1H2, 1D2, sorry. 1H2 is basically known as what? Deuterium. And this is 1H1. So more mass means more priority. Okay. Here also, if we calculate the mass, then carbon, carbon, okay, especially the group which is attached to the double bonded carbon, the stereogenic carbon, okay, the atomic number of that carbon is taken into consideration. Understood? So if the atomic number will be same, then the priority assigned on the basis of atomic weight, then the priority will be assigned on the basis of atomic weight. Okay, the atomic number is 6 for carbon, atomic number is 7 for nitrogen. Which is more prior? It is understood, but here it will be a difficulty. That is why the second rule, which says, okay, atomic weight if in case the atomic number is same. Now rule 3. When both atomic number and atomic weight are same, then priority will be decided by the next joining atom. Will be decided by next joining atom. Okay, like for example, carbon carbon double bond, CH3, CH2, CH3. Okay, CH. Okay, now here you can see carbon, 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 carbon. The groups or the atoms which are attached to double bonded carbon, stereogenic carbon, they all are having same carbon. Okay, but the fact is their atomic weights are different. As a group, their atomic weights are different. So if we consider this group, this and this group, so it will be more prior, okay, and it will be less prior. Understood? Same in case here. This carbon which is attached to the stereojet carbon is having two other carbons directly attached to it. And this carbon is having two hydrogens attached to it. Okay? It is having only one group which is, it is directly attached to only one carbon and other two hydrogens. It is attached to two other carbons. So it is more prior. It is also the E form. Understood? This is the rule number 3. Now, rule number 4. If multiple bonded group attached to the double bonded carbon attached to double bonded carbon, then they are considered in the following manner. As like C double bond O. So it will be written as like that this carbon is attached to, when this carbon oxygen, when it is having two units of carbon single bond oxygen. This carbon is attached to oxygen which is attached to further carbon, okay, and this carbon is attached to further oxygen like this, okay. C triple bond A, then it will be that C is attached to 3A at a time, like this, like this, okay. Understood? For example, now among carbon and nitrogen, nitrogen is more prior. Among carbon, carbon same. Now carbon, then it is attached to the second atom is oxygen. Here also the second atom is oxygen, but the fact is it is CH double bond O. CH double bond O, it is having more number of oxygen atoms, more units of oxygen atoms. It means it will be more prior. This is E form. Okay, is it clear? So this is the CIP rules. Please adhere to the CIP rules. They are very important. Okay. What you have to do, you have to just relate the what we can see. Just relate the atomic numbers and atomic weights of the groups attached to the carbon-carbon double bond. Okay. Is that clear? Now, we are going to talk about syn and anti-isomers. This type of isomerism exhibit by oxenes, okay, exhibit by oxenes and azo compound. Oximes are the compounds which are formed by the reaction of aldehyde or ketones with hydroxylamine. Okay. Reaction of carbonyl compounds, aldehydes and ketones with hydroxylamine. NH2OH. It is a nucleophilic addition followed by elimination reaction. So oxime of aldehyde and oxime of unsymmetrical ketone shows syn and anti-isomerism. Show geometrical isomer. Okay, like for example, if I'll talk about a aldohexene, mean oxime of acetaldehyde, this is known as what? Syn form. Okay, when OH and H are on the same side, it is syn. Okay, and vice versa, it's anti. It's anti form. Okay. In unsymmetrical ketones, they form ketoxime. If OH and the alphabetically alkyl present alphabetically prior, on the same side of double bond, then it is called syn. Okay, and other isomer is anti. Like for example, so you can see OH and this is ethyl. Ethyl is alphabetically, E comes first. Okay, on the same side. This is syn form, and the vice versa of its anti form. Okay. In nitrogen double bond, that is Diazo groups or in azo compounds geometrical isomers in azo compounds. Azo compounds contain nitrogen-nitrogen double bond. Nitrogen-nitrogen double bond, in which each nitrogen is attached to an alkyl or an aryl group, okay, and possesses an unshared pair of electrons. In both of them, they are, and they can be attached to an alkyl group, okay, or can be attached to a aryl group. Both the groups can be same, both the groups can be different. It depends, okay. Azo compounds containing aryl group are more stable. Are more stable. Okay. For example, lone pairs. It is known as what? Cis azobenzene. If the lone pairs on same side. Okay, if they are on different side, like then it is the antiform or the trans. Understood? Now, the geometrical isomerism is cyclic compounds. Fortunately, you can see that the cis and syn is same, trans and anti is same. But the fact is, syn and anti they are given for the multiple bonded system other than carbon, like nitrogen nitrogen double bond or the carbon nitrogen double bond. Okay. Now, some problems I am giving, like if the compound is this, what will be the name? E and O. When see E comes first with M, then actually the name is syn ethyl. So ethyl comes first alphabetically. Ethyl methyl ketoxine. Okay. And what will be the anti? This is anti-ethyl methyl ketohexane. Understood? Now we are going to talk about geometrical isomerism in cycloalkanes. In cyclic compounds, the restricted rotation means the rotation around a carbon single bond. Okay. In 3 to 7 membered ring structure is restricted. Okay. In cyclic compounds, the rotation of carbon-carbon single bond is restricted for 3 to 7 membered ring structure because of the strain, because of the rigidity caused by the presence of other carbon of the ring. Other carbon of the ring, which keep them tightly held which keep them tightly held. Thus, a di-substituted cyclic compound a di-substituted cyclic compound in having two substitution at the separate carbon will also show geometrical isomerism. Geometrical isomerism. Okay. Now, rings having two or more substituents can have different non-interconvertible spatial arrangement. Cyclic rings having two or more substituents, that is why di-substituted, can have different non-interconvertible, can have different non-interconvertible interconvertible spatial arrangement of groups around the ring. Okay. So the minimum requirement, the essential condition for a ring to exhibit geometrical isomerism is that at least two of its ring atoms must have different groups attached to their exocyclic single bonds. Exocyclic single bonds. Okay. Two of its ring atoms must have different groups attached to their exocyclic single bonds. Their exocyclic single bonds. Okay. For example, this is cis 1, 2 dimethyl cyclopropane. Okay. Now, if I want to make trans of it, this is trans. Okay. Two of its ring atoms must have different groups attached to their exocyclic single bonds. This is cis. Okay. This is trans. This is cis. This is trans. So all these are the cyclic structures you can see. Now, to find out the number of geometrical isomers in polyenes, number of geometrical isomers in compounds containing more than one carbon-carbon double bond. In compounds containing more than one carbon-carbon double bond. Okay, that is polyenes. Understood? Case 1. In case of unsymmetrical alkene, if the alkyl groups attached to the carbon-carbon double bond is not equal to R2. Okay, like for example, R1 CH double bond CH, single bond CH double bond CH, R2. If they are not equal, the groups which are attached, they are not equal, then the number of geometrical isomers is 2 की power n, where n is number of double bond showing geometrical isomerism. Showing geometrical isomerism. For example, CH3, CH double bond CH, CH double bond CH, CH2, CH3. One is ethyl and one is methyl. You can see this is R1, this is R2. Both the groups are different. So the number of geometrical isomers will be 2 की power 2, that is 4. Now, case 2. In case of symmetrical alkene, when if R1 is equal to R2, groups attached to the carbon-carbon double bond are same, okay, then the number of geometrical isomers will be 2 की power n minus 1 plus 2 की power p minus 1. If n is even number, then p is equal to n by 2, and if n is odd, then p is equal to n plus 1 by 2. Okay. For example, CH3, CH double bond CH, CH double bond CH. Both groups are same. Okay. Now, the number of double bonds which are showing the geometrical isomer. Okay, I'll change the same example I have given for the first time as well. Okay, I'll change the example. It's better. So here the number of double bonds showing geometrical isomerism is n is equal to 3. And n is equal to 3 is what? It is an odd number. So for odd number, p is equal to n plus 1 by 2. That is 3 plus 1 by 2. That is 2. So it becomes 2 की power n minus 1 means 2 की power 3 minus 1 plus 2 की power p minus 1, that is 2 minus 1. So 2 square, that is 4, plus 2 की power 1, that is 2, means 6. Total number of geometrical isomers will be 6. This is case 2. Okay. So these are the examples for the compound showing geometrical isomerism in polyenes or carbon-carbon, more than one double bond. Okay. The groups attached to are, they may be different, they may be same. Okay. I've already told you the CIP rules. One of the most important thing that during CIP rules, when you are solving the questions of CIP rules, okay, so I'll write down the sequence rules for assigning priorities to groups. Rules I have already discussed. I'm not going to discuss it again. I'm just telling you, okay, like some orders like iodine, Br, Cl, S, CH3 because we had sulfur, okay, fluorine, OCH3, oxygen, atomic number, okay, then nitrogen, then methyl, then tritium, deuterium, and protium, okay. For example, if the two first bonded atoms are identical, then the atomic numbers of the second attached atoms are compared. We have already told you, okay, like this one is more than this one because first carbon, carbon. Then the second is also carbon. Here the second is hydrogen. Okay, hydrogen. The same CH2OH, CH2 and H2, oxygen, nitrogen. Okay, oxygen is more prior than nitrogen. Okay. So we have already discussed the geometrical isomerism, which is the part of the stereoisomerism. Okay, my dear students, I don't think that we are left over with any topic in geometrical isomerism. I just want you to practice more and more, especially the questions. Okay, so we'll meet in the next turn. We'll discuss the optical isomerism. Okay, bye bye. Take care. Stay safe. Stay healthy.